Okay, so now let's talk about the ductility of the steel and why it is important in design. So ductility can be defined as the ability of the steel to exhibit permanent deformations without fracturing. A good measure of ductility is the elongation at fracture, which is given by epsilon sub f. Eurocode 3 specifies a series of requirements on the steel to ensure it has sufficient ductility to guarantee that the assumptions that are made during designs are valid. So these assumptions include the ability of the steel to redistribute stresses or strains, which is necessary, for example, when calculating the resistance to net section fracture of a plate containing a hole. In this case, the elongation at fracture of the steel, of the steel has to be sufficiently large to allow the peak stresses at the edges of the hole to be attenuated and redistributed so that the entire net section is able to reach a stress that is close to the ultimate tensile strength, which is what the equation that gives you the resistance to net section fracture assumes. Another case in which it is important for the steel to exhibit sufficient ductility is when calculating the plastic bending resistance of a steel beam. So in this case, the fibers of the cross-section that are furthest away from the neutral axis are subject to the largest strains, which can be significantly larger than the strain at first yield. So in this slide, you can see the actual stress distribution in the beam cross-section when it reaches its plastic bending capacity. You can see that the portion of the cross-section that is closest to the neutral axis is still within the elastic range, and that the fibers that are furthest away from the neutral axis might develop stresses that are larger than the yield stress because of strain hardening. So this strain hardening is influenced by the ratio between the ultimate tensile strength and the yield strength of the steel. In design, when we calculate the plastic bending capacity of a beam, we assume that the strain hardening that is developed by the steel is sufficient to compensate for the lack of yielding in the regions that are near the neutral axis. And because of this, it is important that the steel has an ultimate tensile strength to yield strength ratio that is large enough to make this assumption valid. This is one of the reasons why Eurocode 3 also requires that the steel should meet a minimum tensile to yield strength ratio. Another reason to specify a minimum tensile to yield strength ratio is because it serves as a safety margin in those cases in which the resistance of the steel is given by its elastic resistance. So in this case, if the elastic capacity is exceeded, the steel section is still able to carry a bit more load as a result of strain hardening. Another situation in which the steel is required to provide sufficient ductility is when carrying out a plastic analysis. In this case, the steel not only has to be sufficiently ductile to allow the cross-section to develop its plastic bending capacity, but it also needs to be ductile enough to accommodate sufficient rotation capacity for the formation of the plastic hinge. Now, let's look at what happened when the ductility of the steel when the yield strength of the steel increases. So here I'm comparing typical stress strain curves of steel grades to S235 to S690. So as Nancy mentioned, as the yield strength of the steel increases, the ductility or the elongation at fracture decreases, and the tensile to yield strength ratio also decreases. So because of this, the use of high-strength steel should be limited to applications that do not require a significant amount of ductility. For example, high-strength steel should not be used when carrying out a plastic hinge analysis. Here I'm showing you the ductility requirements that are given in the current version of Eurocode 3. So for steel grades up to S460, the steel should have a minimum tensile to yield strength ratio of 1.1 and a minimum elongation at fracture of 15%. Also, the ultimate strain has to be at least 15 times the strain at first yield. Now, for steel grades greater than S460 and up to S700, Eurocode 3 Part 112 relaxes the requirements on the minimum tensile to yield strength ratio and the elongation at fracture, and maintains the requirement on the ultimate strain. For the tensile to yield strength ratio, the minimum ratio is set to 1.05, and the minimum elongation at fracture is set to 10% only. Now, these requirements have been found to be conservative and even unjustified. And for this reason, they have been revised for the next version of Eurocode 3. So in the next version of Eurocode 3, all steel grades will be subject to the same ductility requirements. And also the ductility requirements are going to be more restrictive when the design is based on a plastic analysis as opposed to an elastic analysis, which makes sense. Also, the requirement on the ultimate strain will be removed. And this is because research has shown that the effect of epsilon sub u is generally small for steels with low tensile to yield strength ratios. And also because this parameter is not given in the product standard, and therefore, even if I still meet the requirement of a product standard, it would still be difficult to know the value of its ultimate strain. Now, one important thing to consider is that because of the reduced ductility of steel grades greater than S460, they cannot be used when design is based on a plastic hinge analysis. The simplified method that allows for a limited plastic moment redistribution in a continuous beam based on an elastic analysis is also not allowed for steel grades greater than S460. So these restrictions, which are given in the current version of Eurocode 3, are also going to be included in the next version. Now, although plastic hinge analysis is not permitted for steel grades greater than S460, Eurocode 3 Part 112 permits the use of a non-linear plastic analysis, which is able to capture the partial plastification of members along their length and within their cross-section. This type of analysis allows for some limited amount of stress redistribution, but not to the same extent as with the plastic hinge analysis. Now, you should be aware that nonlinear plastic analysis is not used very often in practice because of its complexity, which means that if you want to carry out this type of analysis, you will most likely need to use finite element software. So because of this, when designing a structure that is made of high-strength steel, the most likely type of structural analysis that you're going to be using is the elastic analysis. Now, this type of analysis is also the most common type of analysis that is used when designing structures made of S275 or S355 steel. So this limitation should not be a big problem if you want to use high-strength steel. Now, irrespective of the type of analysis you use, all structures have to be assessed for the significance of second-order effects. So this verification is essentially an assessment of the stiffness of the structure, which tend to reduce when you use members with smaller cross-sections and higher strength. So because of this, you should expect that a structure that is made of high-strength steel is likely to be more sensitive to second-order effects.